My name is Keith Bostic, and my talk today is MongoDB, a new transactional model. My email address is up, and I'll show it again at the end. So I'm going to be referencing some external things, some other talks that you might be interested in, things like that. Please feel free, just send me email. I'm happy to send you a copy of this slide deck. I'm happy to send you, whatever links you want, and of course, answer any questions you have, so please don't hesitate. As I said, my talk today is a new transactional model, and I'm going to cover 3 or 4 different topics. Okay, I want to talk a little bit about motivations and review, kind of get us all on the same page. Why are we here? Why are we doing multi-document transaction? Who cares? What's important about that? And as part of that, I'm actually going to talk a little bit about the release path, how we got here. So this has been brewing ever since the 3.0 release. And so I'm going to talk a little bit about the path we took to get here. And after that, I want to talk a little bit about fundamentally why this problem is hard. Why didn't we just knock it out in 6 months and give it to you in 3.2? And finally, I want to talk about the storage engine, my particular area of interest, and the changes that we made in the storage engine to make multi-document transactions possible. So a little bit about our review and our motivations. Okay, there we go. Fundamentally, it's a question of data modeling. If you look at relational data models, that's it on the far side there. The key word you want to look up in Wikipedia is data normalization. And what it means is that we're going to store each item of data exactly once. If we need more copies of it, we'll reference that original piece of data that we stored. But on the right-hand side, we have document data modeling, which is denormalized. So what we're going to do is instead of putting our data in multiple tables or multiple rows, we're going to put all of our data in a single document. And the bottom line is, in relational models, I kind of have to have multi-document or multi-table, multi-row transactions from the day I start, because otherwise things are simply not going to work. In the document data model, I don't need that. If I can atomically update a document and its indices, I have what most applications need. I don't initially need multi-document transactions. And so when MongoDB was first architected, the applications that it was targeted for, multi-document transactions really weren't a big issue. Okay, so if that's the case, why are we bothering now? What's the big deal? And there are some good reasons, I think. First, you've always been able to do multi-document transactions in MongoDB. You just had to do a lot of work in the application, right? AKA the locking document, right? People have done it. You can do it. But the problem is, it's outside the server, performance isn't that good, and we've shifted a boatload of complexity. So the applications that really do need multi-document transactions, we put a boatload of complexity in there that we really don't want to do. So I would say the principal reasons: performance, we can make that better; complexity, we can make that simpler. But there are a couple of other things, right? MongoDB was aimed at a certain use case in 2010. All right, we were trying to solve a certain set of problems, and that problem was a lot more like tracking advertising clicks on websites than banking applications. But we hope to eventually dominate the entire world, which means we have to handle these other applications. And so we're branching off into use cases that are new to us, and we need to be able to handle those reasonably. There's also an issue of programmer models. I mean, everybody in this room knows when I talk about document data models, they know what I mean. But lots and lots of programmers out there really know about relational transactions. So to the extent that we can meet them at their education or at their model of the world, everything's going to go a lot more smoothly. There's also kind of one really big issue as MongoDB grows. Maybe you don't need multi-document transactions now, but you're going to need them 5 years from now. All right? We're really proud of open source. Open source is very important to Mongo. But let's face facts. It's your data that's sticky. Once you've got 5 or 10 petabytes of data in MongoDB, you're stuck with MongoDB, and we both know it. Right? So what we need to do is give you the confidence that 5 years from now, when you do need multi-document transactions for an application, we're going to be there for you. So checkboxes, vendor lock-in, another reason. Generally, we're focused on application developers here, right? We've always been focused on application developers. And what we're trying to do is make that out-of-the-box experience good, even for these applications that we didn't traditionally handle. We're going to make the applications easier to write. You don't have to worry about locking. You don't have to worry about write retries, things like that, error handling. We'll handle that for you. So we're trying to, again, make the out-of-the-box experience for application developers really good across a broader range of applications. But there's also another audience, which is our internal audience. If we look at the features that we're going to be doing for the next 5 years, 10 years maybe, they start to look in some ways like multi-document transactions. If you want to think about changing a shard key, if you squint a little bit, that sure looks like a long-running multi-document transaction to me. So we have an internal audience here as well. All right. This quote is by the director of e-commerce at Cisco, and I'd like to highlight just two things: the power of NoSQL and mission-critical applications. What we're trying to do here, take the power and the simplicity of the document data model and also give you the wide-ranging consistency, the ACID guarantees that you've had from legacy relational databases. That's what we want to do. So I mentioned ACID. Just to get everybody on the same page, let's briefly go through what we're talking about here because it applies to the rest of the talk. First, the A in ACID is atomicity. Okay? Very simple. We're either going to do all your operations or we're going to do none of them. We'll allow you to group operations and guarantee they either all happen or none of them happen, one or the other. C is for consistency, and consistency is where it gets tricky. The problem is there are principles around consistency, but no database management system in the world follows them. What happens with consistency? Well, you ask me, what's consistency? Well, we promise to follow the rules. And you'd say, well, what are the rules? Whatever we tell you they are. Okay, we're consistent. The problem is that every database management system relaxes consistency to deal with the workloads it wants to handle, right? If you're a banking application, I really, really care that I gave you $5,000 twice instead of once. If you're a web click application, okay, you double counted a web click. I can live with that, right? Our consistency rules and guarantees are really going to be different. I mean, that's why it's so difficult often to do head-to-head comparisons with database management systems, because they simply have different rules wrapped around the applications they're trying to handle. And let me take a real quick detour. The CAP theorem, which we're going to be talking about later today, the CAP theorem is very simple. It basically says you have consistency, you have availability, and you have partition tolerance, and you can pick two of the three. And it's not quite that clean. But what we're talking about today is MongoDB increasing its consistency guarantees, which means we're potentially decreasing our availability, which makes everyone very sad. All right? So there's going to be a trade-off inherent in this work for the next couple of years going forward as we tune this workload, and I'll be talking more about that today. So back to ACID, then there's I for isolation. Again, relatively simple. Isolation is just what different threads of control or different transactions see as they move through the system. So if you have two transactions moving through the system at the same time, do they both see each other's data immediately? You know, if one doesn't update, does the other see it immediately? Or does it see it after the first transaction commits? Or does it not see it at all because they started at roughly the same time? All right, that's isolation. And then finally, durability. You know, if an asteroid hits the Earth, did you lose your data? All right? Or perhaps the more common question is, when my commit returns, was my data durable? Am I guaranteed that no matter what happens, I won't lose that data? And that's durability. Now that I mentioned durability, I want to mention a Mongo World talk that's coming up later this afternoon. Sue Laverso, who's an engineer in the MongoDB Storage area with me, is doing transactions and durability. And she's going to cover in exhaustive detail the entire MongoDB stack in terms of durability. It's going to be a great talk. If you like internals, definitely recommend it. So now, I'd like to talk briefly about the path that we took to get here. First off, this was a multi-year, all-hands effort. We did a lot of work in the storage layer. We did, oh, let's see, here we go. Sharding architecture had to change. We had to introduce a global logical clock. I'll be talking more about that in a minute. We had to give it or had to invent a new replication consensus protocol. There's a talk later today about that. And metadata management, and that's really part of the list. Somebody asked me earlier this morning, you know, what's the hard part? And it's like all of it's the hard part, because all these features have to be surfaced. The driver teams have to know about this. They have to consistently design an API that makes transactions available to all the applications. This is a huge amount of work. It took a lot of years. So we started with MongoDB 2.6, and that was mmap v1, okay? And it had ACID, right? We're talking, well, we've got ACID now. We had ACID then. We're enhancing what we offer. But what did ACID mean with mmap v1? Well, you couldn't have multi-document transactions, and you couldn't have multi-collection transactions. And a transaction really only meant applicable to a replica set. So that's kind of where we started, okay? And now I want to take another small detour. I work in the storage engine group at MongoDB. What's the storage engine? Okay, you can broadly take any database management system and you can divide it into about 3 layers. There's the top layer, which is networking, it's replication, it's sharding, application, query drivers, that stuff. Underneath, in the big chunk, is all the middleware. So business analytics will go in there. You'll have 2 or 3 layers of query optimizers. You'll have multiple language query optimizers, that sort of thing. And underneath all of that is what we call the storage engine. And the storage engine are the access methods, if you've heard that term. A simpler question is, if it talks to a disk drive, it's the storage engine. Okay? That's the engine I work on. That's what I'll be talking about most of today. What does the storage engine do? The most important thing about the storage engine is it's single node. It doesn't care or know anything about networking, it doesn't know about replication, it doesn't know about shards. It worries about a single node. So on that single node, it owns concurrency, right? If you own the data, you probably own concurrency because you're deciding what data any particular transaction might see. So you own concurrency. You also own some form of transactions. Now, it's not like a MongoDB transaction, which is going to cover, you know, lots and lots of different replicas. No. You own a single node transaction, a single change to a single piece of data on a single node. And also, you own durability on that single node, okay? And this is actually one of the really interesting things, and I'll be talking more about it later this morning. But the storage engine has its own notions of concurrency, of transactions, and certainly of durability. MongoDB has a pluggable storage engine architecture, you may or may not know. There are currently 4 storage engines out there. The first is mmap v1, which was the original storage engine done at MongoDB. Facebook did a storage engine which was based on Google's Level DB work that they called RocksDB. Tokutech was a company that did another storage engine called TokuMX that was eventually bought and supported by Percona. And finally, WiredTiger, which is the second MongoDB internal storage engine. So the reason I did that detour was that in 3.0, we added a new storage engine, WiredTiger, to MongoDB. Now, the mmap v1 storage engine was it was based on the Linux operating system's mmap call. Surprise, right? WiredTiger was a much more traditional storage engine. You know, it's a B+ tree with a cache, writing blocks to disk, and it has a write-ahead log as a journal for durability. So a very traditional storage engine. We brought it in for a few reasons. There were primarily, mmap v1 is wicked fast on reads. It is really good at reading. When you start throwing writes into the mix, especially when you start seeing write-mostly workloads, it can't handle that. And so one of the reasons, or the primary reasons I would say, we wanted WiredTiger was to be able to handle write-heavy workloads. Now, it also came with document level locking, which we'd considered ways to do in mmap v1. This meant we didn't have to, and it solved a hard problem for us. There were a few user-facing features as well. We wanted compaction, we wanted encryption, we wanted compression. We also wanted the ability to run entirely in memory. And some of those things were either difficult or perhaps impossible in mmap v1. That's why we brought in WiredTiger. Interestingly enough, though, WiredTiger also included some transactional features. Okay? From 3.0, WiredTiger supported multi-document transactions. It also supported multi-collection transactions. In some ways, what we've been doing since then is surfacing those features, right? Again, this is a single node. That's nothing like what I need to do at the high level of MongoDB. So I'm surfacing those features based on the new storage engine. In 3.2, we didn't do too much transactional work. We did some. We'd had write majority for a while. So you could say, you know, let me know when my write is durable, and I want to wait for that to happen. But we had nothing on the read side. You had no way of saying, I only want to see durable reads. I don't want to see dirty reads at all. And so we added that in 3.2. But we also made a big change because we made the storage engine the default. At that point, when you created a new collection, it was by default in WiredTiger. And so that meant 3.4, we found all the workloads that you had that we had not tuned for, and we spent the 3.4 release doing nothing on transactions but tuning WiredTiger for those workloads. 3.6, we got back to our transactional work. And in 3.6, there were two sides of the transactional work. The first was the features, right? We had to add some features to make multi-document transactions possible. And so logical sessions, that really was the context that we could use for a transaction. For example, if I'm going to say that your reads are going to operate in a single kind of isolation, no matter what node they go to and at a particular time, I need some context that I can pass around. Logical sessions was that context. And we also added a global clock. So we need some way to identify each individual operation or each individual transaction. So we need context, and we need an identifier, and now we can go to causal consistency. Now we can say there is a causal order for your reads and for your updates that we can reproduce and understand for the entire system. So that was the transactional features. But there were also some enhanced consistency fixes. So again, we're adding features, but we're also pushing out enhanced consistency guarantees for the application. And I think the most important one was retriable rights. Until 3.6, what you had to do was you actually had to see if the write failed, and then you said, well, did it really fail, or did it fail after the write succeeded? Maybe I should go look, right? You had to clean that up. You had to decide, well, maybe the write partially succeeded? I don't know. The right place to do that is in the database server. So in 3.6, we added retriable rights so that you know when the write comes back, it either happened at most once, or it didn't happen at all. We also fixed read concern majority. That was originally implemented using a feature called WiredTiger named snapshots. And in 3.6, we fixed that so that we could turn it on in all cases. So essentially, that was a tuning feature. If you're interested in causal consistency in general, how this is done, Misha Tulanev, who's an engineer at MongoDB, did a university video, the implementation of cluster-wide causal consistency. If you're interested in causal consistency, this is a great video. I really recommend it to you. And so here we are. MongoDB 4.0, multi-document transactions, pop the champagne. We have multi-collection transactions as well. As Ali said this morning, it's multi-statement, multi-document, it's multi-everything. Of course, it only applies to a replica shard. We have not gotten to make multi-document transactions work across shards yet. But that's coming. And in fact, in 4.0, we have the storage engine itself knows about prepared transactions. So essentially, if you think what you need for sharded transactions, one shard has to contact some other set of shards and say, I'm about to commit this transaction. Can you guarantee me that you can commit it to? And once all of the shards agree that it can be committed, then we go ahead and proceed. So that's prepared transaction or two-phase commit. The first phase is go check everybody out. Can everybody commit? The second phase is actually do the commit. And if we can do that, then in a future release, hopefully 4.2, but who knows, but hopefully, we'll be able to build the bridge that we need between shards so that we can do multi-document transactions across shards. If you're interested in features and futures, later today, Andy Schwerin, who's a VP engineering at MongoDB, is doing the features and futures talk. And since I'm curious what I'm going to be working on for the next couple of years, I'm definitely going. So that's review, motivations, the path we took. Why is this hard, right? We had transactions in the storage engine at 3.0. Why am I here today? Well, there are two problems that I'm going to talk about. The first one is very storage engine specific. and it's the fact that we've got 2 clocks. All right? There's an old joke that if you have 1 clock, you know what time it is, and if you have 2 clocks, you're never really sure. And the problem is MongoDB until 4.0 had 2 clocks, right? We had the single node storage engine clock and transactions happening there, and then we had the distributed system clock and transactions happening there, and those clocks were not the same. Let me give you an example from replication. If you're not familiar with how replication works, logically it's pretty straightforward, right? We have the primary, and on the primary we have lots and lots of threads concurrently in parallel updating records, fast as they can. Out the back of the primary comes what we call the op log, the operations log, which is essentially a sequential list of changes that will bring a secondary into consistency with the primary, all right? All right, so the secondary gets that op log, usually from the primary, and it applies those changes. Well, that's all well and good, but it cannot possibly keep up if it were to apply those changes sequentially. I mean, you spent good money on your primary, right? That's your hot piece of hardware because it runs really fast and does all the updates. The secondary has to keep up. There's no way it can do it if it's sequentially applying those updates. So what it does the same thing the primary does. It applies them concurrently in parallel. And now we've got a problem because the storage engine is seeing those updates come in and the storage engine is reordering them, right? So the primary op log order, which looks perfectly normal, when the secondary gets done applying those changes, the order is changed. And for that reason, if I now make a query into the storage engine and say, hey, you know, give me the answer for this, I get the wrong answer because it doesn't know the order these changes were applied in. If you think about it, if one transaction changes a document and the next transaction changes that document again, it really matters what order that happens in. And so in this example, the storage engine is reordering those changes. It doesn't match the primary, and the secondary and the primary are no longer consistent. So this is a quote that my boss uses when he gives talks around this or on these topics. And anybody who has looked at this kind of stuff inside a database engine, time is not cause and effect. It is not orderly at all. It's just wibbly-wobbly, timey-wimey stuff that happens. And it all happens at the same time. It gets nasty in there. The second reason that I want to talk about why this is kind of hard is we're increasing entanglement. This really doesn't apply to the storage engine so much as it applies to the upper layers of MongoDB. But getting the right answer on these questions requires a lot of communication. And so in 4.0, we are significantly increasing the entanglement in replica sets. We're significantly increasing the entanglement of shards. I mean, traditionally, in previous releases, there were cases where a shard would simply hit the abort button. I have no idea what's going on. Hit the big red button. We'll start over. It'll all work out. And we can't do that anymore, right? So we are significantly increasing communication at all levels of MongoDB. And this brings me back to the CAP theorem, all right? As we increase the consistency, we risk decreasing our availability. So this is going to be a tuning area for us, I suspect, for quite some time. So that's why it's hard. The first question about the multiple clocks is one that the storage engine specifically had to solve. So let me talk about that in some detail. So MongoDB has a timestamp. It's based on this global clock we added. And it's a Lamport clock, and there's a clock tick. And you take, every time you need to identify something, you take the next clock tick, and you know, that's your identifier, right? That gives you ACID. The ACID guarantees the multi-document transactions for this entire set of systems, right? All the shards, all the clusters, whatever. And interestingly enough, it's the durability here, and it's going to be based on replication, right? So durability at the high layer has enough of my peers seeing this update that I can know it won't go away no matter what happens, right? Essentially, can I guarantee that whoever becomes the primary has seen this changed no matter what happens, all right? That's what's happening at MongoDB's layer. And I'm also, in the next few minutes, I'm going to be talking a little bit about MongoDB like I'm not part of MongoDB, right? MongoDB and the storage engine now, they're a little bit at odds, right? They've got their clock, I've got mine, right? And we're trying to reconcile that. So when I talk about MongoDB generally, I'm now talking about the overarching MongoDB as opposed to the storage engine. I'll try to make that clear, but that might help a little bit. So I've got MongoDB's timestamp, and I've also got WiredTiger's, the storage engine's, transaction ID. And the way it works, as soon as a thread tries to enter the system, it single files them and gives them a transaction ID. All right, there's not a clock here. It's just simply a counter, and you get the next ID, right? And this is going to be ACID for the single node, okay? And this durability here is going to be based on checkpoints and journaling, right? I don't know anything about a peer group. All I know is what I'm writing to disk, right? And if you think about that, that also has to be the final source of truth if everything crashes. If the whole thing crashes, every single system, all we've got is what we've got on disk. Right? So durability here is based on a completely different idea, what I've written to disk that I can get back after a crash. So how do we do it? MongoDB has to win. And the way we did this was we added APIs to WiredTiger that allowed the MongoDB upper layers to pass through these timestamps. And so at some point, those timestamps would simply override the values that the storage engine had internally. So currently, at the top level, the MongoDB timestamp is a 64-bit counter, cleverly enough, right? Obviously, they want that for fast comparison. So what we do is we turn that into a most significant byte first hexadecimal string, pass it through into WiredTiger, at which point we immediately convert it back to a 64-bit integer value so we can compare it quickly again. Why? Well, the concern is, frankly, that when we go to full-blown multi-document sharded deployments, we're going to need more than 64 bits. We don't know if that's true yet. We really hope it's not true, because obviously on modern server hardware, we don't have to lock 64-bit updates. Reads and writes of 64-bit integral values don't require locking. And if we have to change that, if we have to grow it to, say, 128 bits, all of a sudden we're going to have to lock these values, which is going to make everybody sad. Okay? Anyway, so we pass through the MongoDB timestamp. It overrides the WiredTiger transaction ID. Now, let's go back to our secondary example. So we've got the primary oplog order. The secondary takes the oplog. It's applying it out of order in parallel, and then it updates when it's actually updating a record, or at the final moment when it says, I'm committing all these changes, it absolutely sets to a value that transaction timestamp. And now, the secondary update order looks the same as the primary oplog order, and our problem went away. Internally inside WiredTiger in the storage engine, what we're storing is a timestamp with every update. So WiredTiger is an MVCC engine, if you know that term, multi-version concurrency control. And what it really means is that for every, or in a typical key value store, for every key, you can have multiple values. And so the storage engine is going to make a decision when you ask for data. Well, which version of the data do you want to get? Oh, your timestamp 37, you get this version of the data. Your timestamp 112, you get that version of the data, all right? Multi-version concurrency control. And so we had that already based on the transaction ID. We simply had to update that structure so that there was a timestamp on it as well. One really nice thing about this that I think you'll be pleased to hear, in 3.6, updating secondaries was blocking. So the way secondaries worked in 3.6, we would take a bunch of oplog records from the primary, update the secondary, and then we'd satisfy a bunch of read queries because we had these two different clocks, right? So then we get another bunch of updates from the primary and update the secondary, and then we take some more read queries. In 4.0, this is all done in parallel. We can do it all at the same time without blocking. So we're hoping that will give us a very nice performance boost on secondaries, especially on write-heavy workloads. We think we can scale a lot better. So what else can I do with the timestamp? I can update it. I can set it. I can query as of the timestamp. So now MongoDB can come in and say, I want to do a point-in-time read. I want to read the data as of this timestamp. And the storage engine says, great. I'm going to go through, and when I look for the value that I'm going to return for this particular key, I'm going to give you the largest value that I can find that is less than or equal to the timestamp you specified. And we actually have full-blown any point in time reads now. We have not yet exposed that to the application. Actually, we're not real sure how to do that yet. And so all an application can really do is say, I want to see now, or I want to see durable. But we actually have full-blown point-in-time reads in the storage engine. Well, you've probably spotted the problem. So what happens if MongoDB comes to the storage engine and says, I want to see data from, oh, I don't know, April? Well, storage engine doesn't care. It's going to keep all the data that you've changed since April in the cache so it can satisfy that read query. And if you're familiar with cache work, caches are a lot like dams. They can hold a lot of water. And at some point, you hold too much water, the dam breaks, and nothing good happens from that for the entire application. Everything just goes south once that happens. So periodically, MongoDB has to come down to the storage engine and say, hey, we promise not to ask for anything older than an hour ago, or a minute ago, or a week ago, or whatever. This is one of the reasons that it's really kind of tricky exposing this kind of point of time question to the application. How far back can you go? It really, really matters to your storage engine, because they have to keep, or the storage engine has to keep all that data around until it knows that you won't ask for a timestamp that early. So the oldest timestamp. The other interesting issue with timestamps is durability. So I mentioned way back when I was talking about where the storage engine was different from the upper MongoDB layers, is the fact that durability at the bottom in the storage engine is based on writing stuff to disk. And the storage engine's view of the world is, you committed that transaction, I don't know anything about any other nodes, you committed it, I can write it, we're done. All right? Whereas MongoDB at the upper level is going, well, I've only given that to 2 peers. 5 peers have to see it before it's really durable. All right? And network partitions are the same thing, right? The exact same problem surfaces in network partitions. And so again, what we have to do is we have to tell, or let MongoDB tell the storage engine its durability point. And at that point, the storage engine says, well, yeah, I know it's committed, but until it passes a certain durability point, I won't write it to disk. So I will never actually write something to disk that isn't truly durable. And until the 4.0 release, the storage engine was, in fact, writing things to disk that were not durable. And if you know anything about database work, this is not a good place to be. It is not your happy place. Let me give an example. Replication rollback for a single server. So imagine a primary, and it's got the op log that it's generating out the back from its updates. And there are 3 of those changes. They're actually not replicated, not fully replicated. They're in the op log, but not fully replicated. 40, 41, and 42, and we crash. OK, new primary comes up. The old primary comes up again and says, OK, I'm going to be a secondary. It's all good. Give me the op log replacements. And what we'd like to do is just throw away the ones we didn't use, that were never durable, right? And start rolling forward. And now we have a problem because Wired Tiger, behind its back, very carefully wrote 41, 42 to disk because they were durable as far as it could tell. All right? And in 3.6, what we actually had to do was go find those op log records, pull the documents in off disk, and make sure they were OK. And as I said, not a happy place. Not a, really, really error-prone code. In 4.0, we don't have to do that because we know the storage engine never wrote anything that wasn't truly durable. And so now we come up, discard a chunk of the op log, and roll forward, and everything's good. And as an added bonus in here, we're writing 50% fewer log records than we were in 3.6. And that is going to make a difference to write-heavy workloads. Because your choke point often on a single node is how fast I can shove stuff onto disk. And we are writing 50% fewer log records than we were in 3.6. So again, you've probably spotted the problem. If Wired Tiger can't write this stuff to disk, it's got to keep it in the cache. And our dam just got a lot more water behind the wall. Okay? So again, MongoDB has to keep that durable, or that stable timestamp moving forward aggressively to ensure that we never ever get stuck without enough room in the cache. Okay, that's everything that I wanted to talk about with regards to timestamps. The storage group at MongoDB. If you like heavily threaded applications, you like B-trees, you like concurrent operations, you like tricky algorithms, especially lockless tricky algorithms, we're hiring. So the storage group is split between Sydney. If you come to a talk like this, you gotta like that stuff, right? If you're interested in Sydney or New York, we have relatively large groups, 20 to 30 people in both places. And we are definitely looking for people, so please seek me out and let's talk. Thank you. Do we have time for Q&A?
I think we have 5 minutes.
All right, we got 5. Any Q&A? I'm happy to answer anything.
Any questions?
I'm here all day too, so please just find me and I'm happy to talk to you.
There. So hold on.
Thanks, Nate. Keith, that was beautiful. Just curious, is there a consensus algorithm being used between the shards or replicas to ensure that the commits are agreed upon?
The answer is yes, and I don't know any more about it than that.
There's another question over there. Hold on. There's one over there.
You mentioned the log records are reduced by 50%.
I'm sorry?
You mentioned that the log records are reduced by 50% in 4.0 because of the newer transaction model. Can you give us some examples or how?
On how?
Explain how it happened.
Oh, yeah, the question was why and how the log writes decreased in 4.0. It was part of the timestamp work, at least partially. The other thing was a lot of the heavy lifting for recovery moved into replication from the storage engine. And so simply the storage engine doesn't have to have as much stuff anymore. At this point, the only thing we're journaling is the oplog itself. In WiredTiger and the storage engine, the oplog is just another collection. And so the only thing being journaled at this point is the operations log. We're not journaling anything else. And that was, pardon me? Yes, the WiredTiger journal, yes.
One more question.
You said you're checkpointing now. Does it add any delays to the oplog?
The question is, in checkpointing, does it add delays to the oplog?
Yes.
No. The oplog is largely independent of this work. And the only real change in oplog handling is on the secondary, where we are no longer having to stop read queries to apply the oplog. So that should, in fact, make the secondaries be able to deal with the oplog much more quickly.
I see. I have another question. Do you apply ACID transactions to the global clusters now or not?
No, it is not across a sharded deployment.